Hi guys, Audrey here. So today we're going to do a few L'Hopital's rule examples in the cases of 0 over 0 and infinity over infinity. So we're going to start off with these two examples that really look quite similar, but that actually end up being done in completely different ways. So let's look at the first problem here. The limit as x approaches infinity of e to the 2x plus 3 over x squared plus 1. So remember, the first thing that we always want to do is plug in. In this case, we're plugging in infinity, which doesn't really make sense. So what we're really asking ourselves is, what's happening to this function as x gets really, really big? So let's just in the middle here, draw a graph of e to the x. So what we have here, when I plug in that infinity, is I end up with e to the infinity over infinity squared. Well, clearly infinity squared is just infinity. E to the infinity, we can see as we look at this graph, as x is going to infinity, in other words, x is getting really, really big, my function is also, my y values are also getting really, 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 really big. So this gives me infinity over infinity, which is one of the forms that allows us to use L'Hopital's rule. So let's go ahead and do that. So I end up with, we're going to put a little HR over the equal sign for our teacher, and say the limit as x goes to infinity, e to the 2x, don't forget the chain rule, times the derivative of 2x, times 2, over the derivative of x squared, which is 2x. Now, remember, we can use L'Hopital's rule as many times as we want, but before we use L'Hopital's rule, we always want to simplify as much as possible. So in this case, those 2's cancel out. So we're now going to see what happens when I plug in infinity. And the answer is that once again, I end up with e to the infinity over infinity, which is infinity over infinity. So I can use L'Hopital's rule again. So here equals to, using L'Hopital's rule, the limit as x approaches infinity of e to the 2x, chain rule again, times 2, all divided by 1. And now when I plug in, I end up with infinity, and that is my final answer. That is no longer an indeterminate form. Okay, let's go check out this other question. So first we're gonna plug in that infinity. And when we do, we're gonna end up with e to the negative infinity over infinity. Infinity squared is clearly still infinity. We saw that in the last problem. So now the question is, what's going on with e to the negative infinity? So when we go over to our graph of e to the x here, if I'm going to negative infinity, what seems to be happening to those y values? Well, those y values, as we go to negative infinity, are getting smaller and smaller and smaller. They're getting closer and closer to 0. So this actually gives me a 0 over infinity. Now, it's important to remember, 0 over infinity is not an indeterminate form. This is a form that actually makes sense. Crap. Just did a thing. Oops, I don't know what just happened there. This is a form that actually makes sense. So we end up with, this is going to 0 over infinity. And in case we don't remember what that means, this is the same thing as 0 times 1 over infinity. Well, 1 over infinity, that bottom's getting really, really, really big. So the whole thing's getting really, really, really small. So this is 0 times 0, which is just 0. So my final answer here is just 0, and we didn't have to use L'Hopital's rule at all. So here, no L'Hopital's rule was necessary. Okay, so we're just going to do one more quick problem to see another 0 over 0 or infinity over infinity case to see another thing that can happen. So our next problem will be the limit as x approaches 2 of the square root of x minus 2 over x squared minus 4. Okay, so first we want to plug in. And when we plug in, we end up with the square root, 2 minus 2 is 0, 2 squared is 0, 2 squared minus 4 is also 0. So that's 0 over 0. Now, we might be tempted to think of this in the form x minus 2 square root over the square root of x squared minus 4 to see that that is really a 0 over 0. Unfortunately, that's definitely not the best way to approach this problem. If we try to do L'Hopital's rule from the square root of x minus 2 over the square root of x minus 4, what's going to happen is we'll just end up going around in circles. We'll like move a square root to the bottom and another one to the top, and then we'll move the square root from the top back to the bottom and the bottom back to the top, and we'll just kind of keep flipping those square roots around and around and around. So this is not a good plan. This will get us nowhere. From here, we'll put you in a never-ending loop. So don't do it. So what we're going to do instead is remember our limit laws. We have a limit law that tells us that we can actually take that square root and bring it to the outside of the limit. In other words, I can look at this as the square root of the limit instead of as the limit of the square root. So now that 0 over 0 is clearly inside the square root with the limit. So we're just looking at the limit there. So we'll have a 0 over 0 on the inside. We might be tempted to take the big stuff. So remember we've said, if we have a polynomial over a polynomial, we can take big stuff on top, big stuff on bottom. But we can only do that, remember this is key, if the limit is approaching infinity. Here this limit is approaching 2, not infinity. We cannot think of this as big stuff over big stuff. So instead, we're going to go ahead and use L'Hopital's rule, but we're only using L'Hopital's rule on what's inside. That square root is now outside. So that square root will stay there. The limit as x approaches 2, the derivative of the top is 1, the derivative of the bottom is 2x, and now we plug in again and we see that we don't need L'Hopital's rule anymore. We're actually done. So this gives me the square root of 1 over 2 times 2, which is just a half. And that is my final answer with one application of L'Hopital's rule. So be really careful when you have square roots like this involved. All right, that's all for today. Bye, guys.